Hello everyone. In this video we will continue to examine topic 5.3 electric cells, and in particular we will introduce the idea of internal resistance. Alright, so in the last video we discussed how up to now we had been simply assuming that our sources of DC potential difference were ideal cells. And a real electrochemical cell consisting of separated ions, those positive and negative ions flow in the cell to carry the current through the cell as that cell provides energy and current to the rest of the circuit. And in doing so, in a real cell, those positive ions and negative ions do deliver some energy as internal energy of the cell itself or heat loss to the surroundings. That is reduced as much as possible, and in fact, you usually want to use cells where there is not very much energy being delivered to the cell itself. But sometimes it's unavoidable, and in a real cell, a certain amount is literally unavoidable as those ions move from one side to the other. So what we can do, though, is we can analyze this and we can say, all right, well, as a first pass of trying to figure out how much energy might be transferred in that process, how much we're losing, we can model what is going on in here as being simply an ideal source of EMF in series with a small constant resistance known as the internal resistance of that cell. This isn't perfect. If we're assuming this is a small constant internal resistance, we're also semi-assuming that isn't going to depend on the current. And that's not strictly speaking true. But for now, this is a pretty good model to try to figure out what is happening inside the cell as energy is lost when current goes through the cell. Now, consider this particular setup. So we model what is going on inside our cell as follows, with that ideal EMF source and that small resistance R, internal resistance. And then we ask ourselves, in our simple circuit, with our current measured by our ammeter and our potential drop across our external resistance R measured by the voltmeter, we might ask, what's going on? Let's analyze it. So we note that the EMF is equal to I times R total, but now R total is equal to our external resistor plus the internal resistance, which we assume to be non-negligible in this case. As a result, what does that voltmeter actually measure? The voltmeter actually measures what's called the terminal potential difference, which is the potential difference simply across the external resistor. It's the potential difference from here to here, okay? And that's why it's called the terminal potential difference. And you'll note that it is assuming a non-insignificant internal resistance. That terminal potential difference will not necessarily equal the EMF. And in fact, the EMF is equal to I times capital R, or the terminal potential difference, plus I times little r, where this is the internal resistance term. We solve for the potential difference across R, or the terminal potential difference, and we get the following equation. Delta VR is equal to epsilon minus I times the internal resistance. What does this mean in practice? It means that as you crank up the current, as more and more current flows in the circuit, the effect of the internal resistance grows. And the terminal potential difference actually applied to the resistor decreases. EMF is only exactly equal to the terminal potential difference when the current is exactly zero. Otherwise, the terminal potential difference is less. Notice that if we graph delta V versus I, the y-intercept of that graph will be epsilon, our EMF, and the slope of this graph will be negative r. So if you graph delta V versus I for this particular setup, you can pretty straightforwardly read both the EMF and the internal resistance off the graph.